Hello, everyone. Welcome back from the break. Up next is Hemant from CMU, here to talk about security reasoning via substructural dependency tracking.
Right. Yeah, so let's talk about substructural dependency tracking. Okay, first off, I guess, what do I mean by dependency tracking? Basically, if I'm holding a computation in my hand, I want to know how its outputs are affected by its inputs. And this is super useful in a domain like security, where if my computation is processing, say, passwords or cryptographic secrets, I want to make sure that I'm not leaking information about those things to, say, the internet. But these sorts of data provenance and separation properties are also super useful for things like concurrent and distributed systems, and for build systems, because you want to know which files to recompile, and for reactive programming, because you want to know which reactive updates to fire, and for program slicing, and for so many other domains. And in a lot of these cases, there are certain extra questions that sometimes arise that lie just beyond the reach of like what standard dependency tracking techniques can answer. And these are things like, how often do I depend on this data? And like, if I am decided to depend on this data, like, is that dependency guaranteed? And in what order do I depend on these things? And our work is an attempt to answer all these questions in sort of a unifying and satisfying way. And that's like why we did the work. But as far as like explaining how we did the work, I think it's a lot easier to start from the substructural part of the title. In particular from affine types in Rust, which are a particular kind of substructural reasoning mechanism. So if I'm in Rust and I've got this capital S string bound to this variable x, and I pass x to a call to func1, and I pass x again to a call to func2, then I get a type error. In particular, Rust tells me, well, you already consumed x once when you like called func1. You can't consume it. You can't consume it again when you call func2. And this is because data in Rust is ephemeral. You can only consume it a single time. And it's exactly this idea of ephemerality that leads to the kind of like resource reasoning about memory and concurrency that Rust is really well known for. And so we can imagine generalizing from this picture of like only being able to consume things at most once to being able to consume things at most any finite number of times, which might look something like this. Or now we've got a function f that goes from an integer with 3 fuel emojis annotated to an integer. And the idea with the fuel emojis is that each emoji like indicates one allowable usage of the input. So for instance, one valid implementation of f is this, where I can take an input and use it twice in the body. I can also use it thrice in the body. But what I can't do is use it 4 times in the body, because by the time I get to the 4th usage, like the type checker like yells at me and goes like, oh, like you're out of fuel for using the input. Like I can't let you do this. And the important thing to observe here is that it's exactly the number of fuel emojis on the input to this function that dictates its structure, that dictates the necessary structure of its body. And so to get to our approach from this picture, all you have to do is sort of flip it around a bit, and instead of operating by restricting inputs to computations, like with those fuel emojis, we're going to operate by restricting the outputs of computations to create resources. So that might look something like this, where, so sort of analogously to the last example, I've got a function g that now takes a coin int and returns a 3 coin int. And the idea with the coin on the input is that every single time I use the input, it's going to produce 1 coin's worth of resource usage. And the idea with the coins on the output is that it gives me an upper bound for the number of coins that any valid body of G can witness. So again, I'm allowed to use the input twice or thrice, but I'm not allowed to use it 4 times, because by the time I get to the 4th usage, oh, there should be a type error there. But by the time I get to the 4th usage, like the type checker yells at me and goes like, okay, that's not okay. Like this is an error. There should be an error on the 4 coin line. And it turns out I've actually lied to you slightly, because when you flip from the input picture to the output one, what starts mattering for like deep theoretical reasons is not actually like the usage of variables, but rather the running of computations. And this is a really sort of subtle thing that I need to focus on for a bit. So the way to think about this is, well, like the semantics of this coin int type is actually that it represents a suspended computation. So it's kind of like sticking an expression inside a function, so you can like delay its evaluation until like later in the program. And the semantics of these bang operators sitting in front of the x's is that they take the suspended computation, the like not currently running but could start running computation sitting inside x, and they actually start running it. So they like in the literature, this is called like forcing the computation. So they resume its running. In particular, what this means is that like because we're tracking the number of times like the computation sitting inside of x is run, and not the number of times some variable is used, you can for instance like run the computation sitting inside x, bind the result to y, which only produces a single coin so far, and then use y as many times as you want, where y is an integer. Because again, what we care about is not like the number of variable usages, but the running of computations. And so just to keep contrasting a bit here, like the semantics of the coin, of the field emojis, they get consumed by the body of f, whereas the semantics of the coin emojis, they get produced by the body of g. And so like, whereas conventional resources are really like they talk about like memory and concurrency stuff or resources by virtue of like restricting the ways you can use variables or the ways you can consume variables. Our resource reasoning regime is really founded around producing resources or thinking of resources as being produced by virtue of running computations. And this leads to a really nicely complementary set of things that you can talk about within this sort of like flipped resource reasoning regime. And I want to talk about, I want to walk through specifically some of the nice examples of the kinds of things you can talk about under this idea. So we start off, we're going to start off by returning to dependency tracking land. And in particular, we want to track at a very coarse level, like the amount of information that we're leaking about some password, say. So this password tracker module is going to start it by declaring an affine resource lock, where affine, all that affine means is it's sensitive to quantity. So like the number of these lock emojis that appear in a type matter, it's very, very similar to the coin from before. So we declare this affine resource lock. We also declare a method check that takes in a password attempt as a string and gives us back a Boolean indicating whether we got the password attempt right or wrong. And that Boolean is annotated with a lock. And so when we go to use this thing, if we call check once, we induce a single lock. If we call check twice, we induce 2 locks. But if we call check twice and only annotate a single lock and only annotate a single lock in our type, the type checker will complain and it'll say, well, I don't know what to do with this because I can see that you depend on more password data, namely like password data resulting from checking it twice or from attempting twice. Then you've declared in your type, so I can't allow this like type error. So you can't do that. But something you can do is in this first line, it's perfectly fine to overestimate the amount of password information you depend on, right? So even though you only called check once in the body of this let, it's perfectly okay to go in the type and say, actually, I've produced or I depend on 2 lock emojis worth of information about the password. And the reason for this is due to a principle called strictness. And strictness is all about whether you can get from a resource context without some, or whether you can get from a set of resources without some dependency in it to a set of resources with a dependency in it. And with locks, this is always okay. We can always give ourselves as many locks as we want. But we can imagine a resource, say diamond here, for which this is not okay. And it turns out this leads to like dropping the ability to do this is really interesting. It leads to a certain kind of authorization reasoning. So this module authorize exports a strict resource diamond, where again, strict means that you can't give yourself a diamond for free like you could give yourself a lock for free. So you need some way to obtain it. And the way to obtain it is to call this authenticate method that takes in a password attempt as a string and returns me a unit with nothing on it if I got the password wrong, or a unit with a diamond on it if I got the password right. And the idea with this is that the only way for me to get a hold of a diamond is to actually successfully authorize myself. Right? If I'm holding a diamond, it means that at some point in my past, I successfully called the authenticate function and retrieved a diamond from it. So if you have some like sensitive information or if you have some sensitive functionality in your program that like you need to gate behind authorization, all you need to do is mention a diamond in one of its arguments, and this prevents anyone who hasn't successfully authorized and therefore doesn't have a diamond to present to it from calling it. And so like one example sort of usage of this is to call authenticate against some password attempt. And if you get the left one, namely the unit with nothing on it, then you got the password wrong, and maybe you run some like error handling or cleanup logic. But if you get the right one, then we're in business, right? That's the exciting case. And you get this token back with this unit that's got a diamond annotated on it, and you can staple the diamond from the unit onto this integer 4 using this like backwards squiggly arrow operator, and then you can pass that integer into the secured function to like call it successfully and like do whatever you want. So that's cool. And our last example is going to be what are called like privilege dropping protocols, or like the seccomp system call in Linux. So it turns out there's this like really popular pattern across a lot of really sensitive software. So I guess we just sort of talked about web browsers. So something web browsers do is, or a pattern that a lot of sensitive software follows is at startup they need a lot more permissions, or they need access to a lot more resources than they need later on in their execution once they've like reached their running state. So for instance, like when your web browser or your web server starts up, it needs to like maybe create temporary files and like take locks on a bunch of system resources and like spin up network sockets and all this stuff. But once it's reached its running state, it really doesn't need most of that. So what it does is it tells the operating system, okay, like I've reached my sort of like steady state now, and from this point forward, I'm only going to use some little carved out piece of your API surface. And I'm forging this contract with you right now, saying that if I attempt to like tread outside this like low privilege part of your API surface, like you should like terminate my process immediately because I've been compromised. So it's kind of like a self-protection mechanism that your web browser does in order to like stop itself from, in order to stop any compromise of it from being like too like damaging. And it turns out we can model this sort of thing in our system by using what are called immobile resources. So we start off by declaring two immobile resources, drop and high. And the actual situation is ever so slightly more complicated. I'll refer you to the paper for that. And we also declare a structural resource low. And all that structural means is it's just like totally unrestricted. So immobile means that like the ordering of these resources within a resource context matters. So you can't just like swap them around freely, which is something you could do before. And structural means it's totally unrestricted. It's like not affine, it's not strict, it's not immobile. There's no restrictions on it. And we declare like actual operations corresponding to each of these resources. So we have a drop operation, a high operation, a low operation. And the way to use this thing is in the type, you go in and say, well, like the high resource has to occur before the drop resource, which is significant because they're both immobile. And then we've got a low resource sitting in there. So for instance, you can do high, low, drop, low. That's totally fine. You can also do low, high. And just never call drop. That's also totally fine. But what you can't do is call a high operation and then drop privileges and then do a low operation and then finally like try to do another high operation, because this is like no good. Like the type checker looks at this and goes like, well, this doesn't match up with what's declared in the type, because in the type you told me like after dropping privileges you would not do another high operation, right? Because high occurs specifically before drop. So this is no good in the type, and the type checker like says to like go back to the drawing board on this one. And the thing to take away from all these examples is that like the production perspective very naturally characterizes a different range of resources than the consumption one, right? So with this like password leakage example, it's very natural. Oh, sorry. With this password leakage example, it's very natural to think of like a computation handling some secrets as like producing information about that secret, right? It's not as obvious how you would characterize like information leakage as a matter of consumption. And again, with capabilities, right? Like a capability is something that's like produced by an authorization computation. It's again like not very clear and actually quite difficult to characterize it as a matter of like somehow consuming a resource. And the picture is slightly less clear with this like seccomp example or this like privilege dropping protocol example, because people have done lots of great work on security protocols in the literature. But it's interesting to wonder, like, you could use maybe object-oriented linear type state to emulate the same sort of example that I just gave. But it's interesting to wonder about the ergonomics of like maybe passing around the entire operating system kernel as like a type state object, so you can like enforce this kind of like privilege dropping protocol on it versus just like isolating the few operations from it that you care about with these resources and like just declaring ad hoc like an ad hoc protocol right then and there and like reasoning about it locally as we did. I would argue like what we did is a bit more ergonomic in that sense. Okay, so I want to move on to some formal properties. In particular, it turns out that we get a 3-for-1 deal on quantity, capability, and protocol safety. And to explain like why this is the case, I have to pull back the curtains a little bit. So when I discuss this idea that like you can get from a resource context without a daemon in it to a resource context with a daemon in it, maybe, or you could imagine doing this. And then we subsequently dropped the ability to do this for free. What was really happening underneath the hood is like sort of maybe by default, like you can gain resources for free, and there's this like inequality or rewriting relation that says, well, like a resource context on the left hand side without a daemon can be freely rewritten to a resource context on the right hand side with a daemon in it. And when we dropped the ability to do that, we made this rewriting relation or this inequality relation like more strict. Right, so we ended up with, well, I guess it's kind of a pun, but we ended up with a strict resource daemon. And again, when we restricted this, like the ability to smush two lock emojis together into a single lock emoji, or to rewrite two usages of something into one usage of something, we ended up with an affine resource lock. And likewise, when we made it so that you can't commute the high and drop resources to be the same thing as like dropping and then doing a high operation, we ended up with these immobile resources because we strictified this rewriting relation or this inequality relation. We made it more sort of draconian. And the thing to take away here is that like all of our reasoning principles are moderated exactly by this like inequality relation, and it operates based on which reasoning principles are active for each resource that it's in these resource contexts. And sort of with that in our back pocket, we can state soundness. So soundness can be read off as, well, if I've got a well-typed program with some expected resources, A1 and A2, then that program evaluates down to a value. So I like use the bang operator on it, and I push it all the way down to a value. And as I push it down to a value, it produces these dynamic resources, B1, B2. So like as it computes, it's like these are the resources that it's actually like producing. And whatever resources it's actually producing as it computes are compatible according to this rewriting relation with the resources that were specified statically. So this is like a very classic like soundness theorem of like whatever your specification says statically is a conservative over approximation of whatever whatever like actually happens when your program computes. So like your like whatever you say statically like reflects what happens dynamically. So you can use this to get capability safety, and to do that, we'll need to sort of be more formal about what a capability is. So Linden in 1976 defined a capability as a token used as an identifier for an object such that possession of the token confers access rights for the object. You can think of it as a kind of ticket. So the fundamental safety property for a capability is this idea of like unforgeability, right? Like you must not be able to obtain a capability in a dishonest way. The only way to obtain a capability must be like really honestly computing one without any tricks. And just as an aside, like he goes on to later say like reproduction of capabilities is legal, right? So it's interesting because he's sort of explicitly saying here that like that capabilities are not an affine resource, right? So even like 50 years ago, like they were already thinking of capabilities in this like resourcey way, and our work is sort of like like among the first to sort of formally realize this. But okay, that aside, you can think of the safety property for capabilities as follows. So if I have a well-typed if I have a well-typed program under some resources A1, A2, including a diamond, where diamond is strict, then if I push that program all the way down to a value, I evaluate it. Then it produces dynamically these resources B1, B2, where the dynamically produced resources include a diamond somewhere within them. And the reason for this is pretty simple. So by soundness, we know that the dynamically produced resources are conservatively over-approximated by the statically specified resources, which themselves include a diamond. And we know by strictness that we can't rewrite a resource context on the left-hand side that doesn't include a diamond to a resource context on the right-hand side that does include a diamond. So the only way for us to have the rewriting or inequality relation on the left-hand side by soundness is if the B1, B2 resource context already contains a diamond, because there's no other way for us to obtain one. Okay. Quantity safety follows really similarly. So just reading it off, it says if I have a well-typed program under resources A1, A2 with n locks, where the lock is affine, then if I push it down to a value, if I evaluate it all the way, then it produces dynamically some resources B1, B2 containing k locks, where k is upper bounded by n. And the reason for this is again really similar. By soundness, you know that the dynamically produced resources are conservatively over-approximated by the statically specified resources, and you know by the property of like affinity that you can't smush together, or you can't rewrite two locks into a single lock from going from the left-hand side to the right-hand side. So the only way for the inequality relation on the left-hand side to hold is if the B1, B2 resource context already contains less locks than the A1, A2 resource context, i.e. the A1, A2 resource context over-approximates it. And of course, if you add strictness, then the bound becomes exact. So k has to equal n, because not only does the A1, A2 resource context have to contain more locks than the B1, B2 resource context, there's also no way for the B1, B2 resource context to like give itself more locks for free because of strictness. So the B1, B2 resource context has to contain exactly that number of locks, i.e. the program has to exactly witness that number of locks as part of the evaluation. So our final soundness theorem is this. Is protocol safety, and there's a lot of different ways to state this, so I'll just state like a little fragment of it. So basically, if we have a well-typed program containing resources A1, A2, or A1 and A2 are immobile, and if I push it down to a value, it produces resources B1, B2, where one potential satisfying dynamic resource context under protocol safety is one where, in the most boring way, A1 and A2 appear right at the beginning of the resource context. So basically, it's this like relative ordering property where dynamically the A1 resource has to be produced before the A2 resource as the program computes. And this is and the proof sketch for this is analogous from soundness, weakening, correction, exchange. And there's a lot more in the paper. So there's 2 further reasoning principles I haven't mentioned here, which is interesting besides immobility, affinity, and strictness, which is interesting because conventionally in the PL community, people think there's only 3. There's lots of really deep connections to modal logic and crypto semantics. The way we did the proof for this is really general and nice. So check that out. And there's lots more examples in the paper as well. But really the takeaway from all of this is that like this new view on resources sort of newly unifies a set of old tools under a single framework, right? And the reason this is important is because like heretofore to like have all these different features in a single language, you had to like cook them all up from scratch individually, and they had to be sort of ad hoc features. Now you can have them all under a single sort of like unified sort of like you only have to understand how this one thing works, and then you get all of these things and many more that we mentioned in the paper for free. So that's pretty cool. Great.
Thank you so much for that presentation. Feel free to put any questions in the chat, anyone, but while we're waiting for some questions, I had one, which was, have you thought at all about what it would look like to like enforce maybe like having like only weakening and like not having contraction or mobility for like all of your resource variables, or like only have contraction but no weakening or mobility?
Yeah. So I didn't mention it in the talk, but it's actually possible to for each resource variable, you can freely choose which of weakening, contraction, and exchange you have. So you're welcome to flip on like okay, for this one I've got exchange and contraction, or exchange and weakening, or I've only got weakening, and then for these other ones I've only got weakening, and you can enforce for an entire resource context that they all satisfy some particular configuration of substructural modes. Basically, it's a level of generality that I didn't want to get into in the talk, but yeah, it's totally possible, and that's actually one of our like the ability to do this is actually one of our core contributions, because we connect it really nicely to like the Kripke semantics with the quantifier connectives and like adjoint logic and linear nonlinear logic.
Thank you so much. Doesn't look like we have any other questions. But thank you. Yeah.
Okay. Thank you.